All right, so we are continuing our review, and today our focus is rational functions. And so these are basically anything with our fractions, polynomials divided by other polynomials. However, it is helpful to start with a quick factoring recap because if we're dealing with these rational functions in factored form, it's a lot easier for us to simplify some stuff. So, real quick, just going to use three different methods to factor here. This first one we can handle with the sum and product puzzle. We're going to multiply to -10, and we are going to add up to -3. And the number combo that works for that will be a -5 and a +2. That matches both of those. So our factored form there is just going to be x minus 5 times x plus 2. Example 2, we can handle our difference of squares. We notice that we have a square up front, and 9 is a squared number where we can take 3 squared and get 9. So that's that instance of x plus 3 times x minus 3. And lastly, this is a combo of doing greatest common factor and our sum and product. I notice that I can divide out a 2 from each of these coefficients. So if I divide out a 2, I'm left over with x squared plus 7x minus 12. And then I have an instance of our sum and product puzzle where I can multiply to -12, add to 7. So multiply to -12, add up to +7. And in this case, it would be -4 and -3. And so my final factored form would be that 2 out in front, x minus 4, and x minus 3. That should be just one minus sign there. So to apply this to our rational functions, okay, we can kind of if we rewrite this rational function in factored form first, then we can simplify. And later on in your problem set, this will make things a lot easier for you. So on the top here, first thing I'm going to do, I'm going to pull out a greatest common factor of 4. It looks like I can pull out. I'm left with x squared plus 3x minus 10. On bottom, I have my difference of squares with 5 times 5 is 25. So I got x plus 5 times x minus 5. And then I can go ahead and factor that top one more time, where it looks like I'm multiplying to that -10, adding up to that +3. So it's pretty close to what we did before, just with those signs reversed from example 1. In this case, I just have x plus 5 times x minus 2. And on bottom, I still have my x plus 5 times x minus 5. And so you'll see that we have this x plus 5 that shows up on top and bottom. I can cross that off on top and bottom and just be left with a simplified version up top of 4x minus 8 if I distribute over that x minus 5. Much simpler way of writing this rational function. So one thing that is special about these rational functions is they have discontinuity because division is involved. So the first type of discontinuity are horizontal and vertical asymptotes. I'd recommend kind of jotting these in your sketch here. This is a horizontal asymptote here in red. This orange one is a vertical asymptote here. And we can find these by simply graphing and looking for those horizontal or straight lines where our graph never touches. It's easy to visualize that by typing in x equals or y equals to write in a vertical or horizontal line. There's also a point of discontinuity or hole, which will just show up at an instant in our graph. We can either use a table or search with our cursor to find that, but a hole is kind of shown right here in our image. For example 5, quickest way to find all of these different discontinuities is to just graph our equation. So let's do that real quick. F of x equals, and whenever I'm working with these, whenever we're working with these rational expressions or equations, I like to throw the fraction in first. It helps me type it out easier. So then I get 4x squared up top minus 4x minus 8. And on bottom, I get x squared minus 5x plus 6. And I'm going to have to zoom out here a little bit to see what's going on. So first thing I want to find is a horizontal asymptote. So I'm going to check my different y values. And it looks like here, maybe around 5 or 6 or maybe even 4, I have a horizontal asymptote. I'm going to type in y equals 5 real quick to see if that works. And you'll notice that right here, my line intersects. So that is not the correct spot. I'm going to have to shift that down. If I check out y equals 4, you can easily see that that's a horizontal asymptote at 4 because my graph doesn't hit it. So I can kind of write that in. Hey, where's the horizontal asymptote? It's at y equals 4. The vertical asymptote, I can do the same thing but using x. So if I kind of inspect my graph here, I'm going to zoom in a little bit so I can see roughly where I'm at. Maybe I'll try this at 4 as well real quick. X equals 4. Well, didn't quite nail it because I have an intersection up here that my graph hits, so that's clearly not it. I need to shift it to the left. X equals 3. That seems to be pretty good where my graph is never going to touch that line, x equals 3. So my vertical asymptote, x equals 3. Lastly, we need to check and just see, hey, is there a hole at 2? We can do this a couple different ways. We can either add a table in our function. So if we go to the settings and click table, okay, it'll list a bunch of possible values. We're going to notice that, hey, at 2, my equation is undefined. So if I see that that's not where my asymptote is. My asymptote is at 3. And if I were to click and drag here, let's pretend I didn't have the table, and I just clicked and dragged to find x equals 2. Well, once I hit it exactly, if I can hone in there, oh my gosh. Boom. My cursor changes to a hole. It lists as undefined, and therefore I do have a hole here at x equals 2. So I can just write in yes. So quick note, we can also find horizontal asymptotes in holes by factoring. This is just quick review. If I wanted to rewrite this function in factored form, I would have my, on bottom, I'd use that sum and product puzzle. I'd have x minus 6. Oh, sorry, not that. It would be x minus 3 times x minus 2. Up top, I would have a 4 factored out for my greatest common factor. Then I'd have x squared minus x minus 2. And this can be rewritten in factored form as 4 up top, we get x minus 2 times x plus 1. And on bottom, we get x minus 3 times x minus 2. And this is where our horizontal and, vertical asymptote, I should say, and holes come from is this idea that, hey, I cannot divide by 0. So when x equals 3, we're going to have a vertical asymptote. Our graph doesn't hit there. However, we also can't divide by 0 with this x minus 2. When x equals 2, we have another discontinuity or a spot where we can't divide by 0. However, that x minus 2 also shows up top. So if we were to simplify it, it'd cross out, hence the hole instead of just the vertical asymptote. Moving on, we handled a bunch of operations with rational expressions. In each of these cases, make sure you're kind of following this idea that factoring is going to help us deal with all of these. However, in all of these operations, I just want to quick recap the rules, and you'll run into some higher level problems later on. With multiplying, we just go straight across. So if I want to set up this problem, all I'm going to do is rewrite it in factored form. I have x times x minus 9 and x plus 2 times x plus 10. Some of you might like using the box method to work on the bottom problem. I'm going to kind of do this in one step here. Up top, I get x squared minus 9x by distributing in. On bottom, I go x times x is x squared plus 2x. Then we go plus 10x. And lastly, plus 20. And then I can simply combine like terms to get my final expression where I have x squared plus 12x plus 20 on bottom and x squared minus 9x up top. Some of our answers might be just written in factored form, however, so depending on the question and the context of the problem, just be on the lookout for that. Dividing, we're going to do keep, change, flip, and then we're going to kind of work through the problem exactly the same. So for my keep, that's going to be just this first expression here, this first rational expression or first fraction. So I'll rewrite that. We have 6 over x minus 5. My change, we are going to change that division sign to multiplication. And lastly, that flip, that's our last rational expression that we're going to flip the top and the bottom part. So I have x plus 3 and x minus 8 now at the bottom. And then we can multiply straight across to work through our problem. So we have 6 times x plus 3 and x minus 5 times x minus 8. And if we do that and actually work it through, we'll get 6x plus 18 on top because we're distributing that 6. It's going to multiply with both of those. And on bottom, we'll have x squared minus 5x minus 8x plus 40. And that comes from all of my distribution here, x times x, negative 5 times x times negative 8, and negative 5 times negative 8. And we can just combine like terms in that last part to get x squared minus 13x plus 40 on bottom and 6x plus 18 on top. Adding and subtracting. So two different cases here. If we have the same denominators, it's super simple. Notice how we have both x minus 4 and x minus 4 on the bottom. So we are just going to keep those the same. And then so what happens is we are going to add and subtract at the top. So I have 3x minus this entire x plus 2. And I threw this in parentheses because I want to make sure this minus sign is being taken into account. That would simplify it to 3x minus x minus 2 if we distributed that negative sign in over x minus 4. And so we would get 2x minus 2 over x minus 4 as our simplified version. If the denominators are different, notice how we have x plus 1 and x minus 2 here. We are going to kind of use that quote-unquote butterfly pattern in order to set up our problem. So I'm going to kind of make this a little bit wider this time because I know it's going to take me a little bit here. I can kind of start by doing that cross multiply up top. We have 3 times x minus 2 up top. We have a plus sign because that's what is in our problem we're adding. Then I have this 1 times x plus 1 also taking place up top. And lastly, I'm just going to multiply across on the bottom to get my bottom problem, x plus 1 times x minus 2. And then we just need to do some simplifying steps here. So my red expression is going to be 3x minus 6 because I'm distributing that 3 in. It's hitting both of them. And I'm adding it with this orange expression. That 1 distributed in just gives me x plus 1. And on bottom, we get x squared plus x minus 2x minus 2. And just one more step to simplify the denominator of my rational expression. We get x squared minus x minus 2. And we can also simplify up top as well. 3x plus x equals 4x. Negative 6 plus 1 equals negative 5. All right, so solving rational equations. This one, the big step here that I'm going to highlight for you is we want to cancel out the denominators by cross multiplying. And I'll just hit this word cross multiplying here. In example 10, pretty straightforward. We want to kind of multiply that 3 by 2x minus 1. And 4 is going to multiply with that x plus 2. Canceled out the denominators on both sides, so we just have a straightforward expression here. And then we can start solving. So it helps to distribute, so we need to go 3 times 2x, 3 times negative 1. That'll give us 6x minus 3. The 4 times x times 4 plus 4 times 2, we get 4x plus 8. Now we need to start using algebra to solve. Let's get all variables to one side first. I'm going to subtract 4x, subtract 4x. And that will leave me with 2x minus 3 equals 8. I'm going to move that 3 over by adding it to both sides. I get 2x equals 11. And then lastly, divide that 2 from both sides. And 11 divided by 2 will be 5.5. So the last thing to check here is for extraneous solutions. And let's go back to the idea we cannot divide by 0. So if I were to plug 5.5 in for x on this side of our equation, we would get 7.5 in our denominator. That would be okay. If I were to plug 5.5 in for this x, we'd get 2 times 5.5 is 11, minus 1 is 10. So that's fine too. We are okay. That's a valid solution. This will come into play in example 11, which is a much longer problem. First thing I want to do is I want to make sure that this 9 is rewritten as a fraction. So a whole number 9, we can pretend that we're dividing by 1, which then helps us do our cross multiply step. We have 9 times 3 minus x. And that equals our cross multiply step of 1 times x squared minus 9. I can simplify both those sides through distribution. We get 27 minus 9x equals x squared minus 9. Now to solve this by hand, which I would not recommend doing, I'd recommend graphing a problem like this. You can recognize that we have a polynomial with a square. So we need to move all numbers to, or all terms to one side of our equation in order to set to 0 and find those zeros. So I'm going to add 9x to each side, add 9x. So that leaves me with 27 on the left equals x squared plus 9x minus 9. And now I'm going to subtract that 27 from both sides as well, leaving me with just 0 on the left, and x squared plus 9x, and then negative 9 minus 27. That gives me negative 36. Now I need to rewrite in factored form in order to find those zeros. So if I'm multiplying to that negative 36, adding up to to positive 9, I think the number combo that works here is going to be, is it 12 and 3? Yeah, it'll be 12 and 3 with a positive 12 and a negative 3. That'll get us that negative 36. 12 minus 3 gets us that positive 9. So we get 0 equals x plus 12 times x minus 3. And that means that our zeros here, or our solutions, are going to be x equals negative 12 and x equals positive 3. So the last thing we need to do here is check for extraneous solutions. And if I look at this and I plug both these x's back into my equation, if I do x equals negative 12, I'll get 3 minus negative 12 will be 15 on the bottom. That's okay. That's legal to divide by a whole number. But if I plug in this x equals 3 into my equation here, I'm going to have 3 minus 3, which gives me a 0 denominator. So that is not okay. I'm going to cross that out. Let me grab my pen here. That gives denominator of 0. So our only answer here then is x equals negative 12. Now, with both of these are super long processes. I'd recommend solve by graphing. And let's get some good practice with that. Plug each side in the equation as separate functions, locate those intersections. For example, 10, let me clear out my stuff. I got f of x equals, I'm going to write the fraction first, so 3 over x plus 2. And my second one I'm going to write is g of x equals, here's my fraction, 4 over 2x minus 1. And you can see that here's an intersection right here. X value is 5.5. Boom, we're good. For the second one, let's rewrite these real quick. I'll delete that. I'll delete that. Up top, we have x squared minus 9. And we have 3 minus x on bottom. That's my left side. My right side is just 9. And if I look here and zoom out, I only have the one intersection. It's at negative 12. We don't even have an intersection at that x equals negative 3 because we actually should have a discontinuity there where the graph is undefined. So that's just a quick way to, if you were concerned about this last step, checking for extraneous solutions, we can avoid that simply by solving these things graphically.